Recursion is one of the most powerful concepts in computer science. It's profound. It's this idea that you can define things in terms of themselves. And we have two forms that we're going to explore today: recursive structures, which are classes and objects and data that we'll have in memory. And these classes and objects will be defined in terms of relationships to one another. And then we have recursive processes, which are functions and methods. And these are ways of defining functions and methods that actually call themselves to carry out the iteration or the algorithm of the work that we're trying to do. Recursion is something that exists in life. We are defined in terms of our parents, right? And one human is connected to the next human in terms of a lineage by who their parents are. Similarly with animals and plants and so on. So let's take a look at recursion in a conceptual sense first, and then we'll dive into how do we actually start to explore this in code. Now, let's just jump right into a structure, and then I'll give a caveat when we get into code. So when we're thinking about recursion, our simplest form of a recursive structure is what we call a linked list. And a linked list is this idea that we'll have a node, right? So this is a node, and this will be an object of type node, and it will have some value associated with it, like let's say the value 110. And it will also have a reference. And for our purposes, in memory, we would think of this as, ID, whatever the next value is, and we'll come back to this. But for now, I'm going to keep this as a pointer to somewhere. So this is a pointer. And, every list has to have some ending. So let's imagine that this ending is just none, right? So this is our simplest linked list, right? And we think of this as the value. And we'll see that we have an attribute for our class named the value. And we have, this is our next pointer or our next reference, right? And so this is a list with a single item in it. Now this isn't actually the simplest list. I was a little bit of a gotcha. The simplest list is actually this one, right? Where it's an empty list. So our simplest list, I might even we'll write a progression here, is just none, the empty list. And you can kind of imagine what a list with two items in it might look like. So let's imagine that we had a list where 110 was followed by 210, which would be potentially the next course that you take in computer science. So we would have a node 110, and its next would be pointing to a node with a 210 value in it. And you can imagine storing different kinds of values, and its next would be pointing to none. Now I've got this interesting challenge here. Notice that, so let's actually just make a note of this. So length 1. Notice that we're seeing something here that we just now have the ability to represent as a type, but we've got this problem, and let me highlight this problem. So notice that our next value here is either pointing to another node or our next value is pointing to none. So how can we express a type where it can be one type or another? Well, we just learned about type unions. And so we can imagine that the type of our next attribute is going to be, let me actually get this in pen, next, would be type node or none. And the big idea here is, think about, we're defining this inside of a class named node. And we'll also have a value, and in this example, we'll have this value type int, right? And so this would be our simple structure of a linked list, right? This would be the attributes we need in order to represent a linked list node. And this is where we're seeing the recursion, the structural recursion, right? So we're seeing here that a node class has an attribute that can reference another node. And that object can be an object that references in its next attribute another node and another node. And so this is where we get the power of creating a linked list. We can chain these together. Now, you're probably wondering, we've already got the concept of a list in Python. Is it built in the same way? Well, not exactly. And you might be wondering, where are there uses of a list like this? This seems like it's going to be more work for us to actually use than just Python's built-in list. And yes, your instincts there are going to be correct. This is going to feel a little bit more tedious than working with the list that we've shown you. And typically for most problems, you want to use the list that we've shown you for reasons that are, it is simpler. In memory, it actually takes up a little bit less memory because all of your items are organized together in memory. So why learn about recursive structures at all, and why start with a linked list? Well, this is a lot like any introduction to a big, powerful concept that can become, much more complex and much more beautiful, frankly, than just a simple list. These are the fundamentals, and you can't really work your way towards the bigger and more powerful ideas, such as trees and graphs, until you have a solid handle on working with something simpler, which is lists, a linked list like this. Now, just to give you an example of why is this powerful, where might you see the idea of a recursive structure in the real world, I'm going to use a little bit less sophistication here and imagine your file system. So on your computer, you've got your folder. Oops, let me go back to pen. You've got your folder, and it's your home folder, and your home folder has another folder, and that's your desktop and your documents and maybe your photos, right? So you've got your folders here, and then each of these might have, file A, photo B, and so on. And notice how we have this tree structure. Your docs are going to have some items in it. Your photos are going to have a bunch of items in it. And maybe you've got folders within your photos folder. You've got your organized by your trip that you took, and it's got items in it. And so this ability to represent a tree also is an idea that is a recursive structure. So your directories or your folders are related to one another in a recursive way. A folder can contain a folder. Therefore, you can have a folder containing more folders and so on, until ultimately you reach some point where the recursion stops. And so in a file system, that what we call the base case, or the terminal value of this recursive structure, is when you have just plain files, or maybe you've got a folder that has no files in it, right? But ultimately, the structure needs to reach an endpoint, and it needs to reach what we're going to see when we're processing these values is called a base case. And the base case is where we just stop the recursion. There's nothing more for us to do, right? And in a structure, our termination on a linked list is going to be when we reach a none value, right? So you can imagine just very quickly, the file structure is a little bit different. Each of these directories, say, if you had a directory object or directory class, you could imagine, and this is just a very quick scribble, you could have a children. And this is sort of a funny notation in programming, but in trees, it's often that we'll call the nodes which come after another node children. So if we imagine home as a parent node, then its children are these three. And then desktop, its children would be these two values, and so on. So the way that we would be able to represent this is children would be, say, a list of directory. Let me actually move this over so that it all fits. Or file, right? And so that union type says, okay, we can have a children, which is a list of directories or files, and then there would be other attributes, of course. And this is, again, another example of a recursive data structure. We're not going to go into trees here, but this would give you the ability to make a tree. You'd also need to have a class for file and so on. But this is fundamentally on, with a little bit of additional details, certainly, this is how your file system works under the hood. It's a recursive structure. So with that, I think rather than trying to talk through what is a recursive process, Actually, let's use this example really quickly to motivate the recursive process that we're going to do, that we're going to implement together in code. So let's imagine we're trying to write a sum algorithm for a linked list. And this is the concept that we're trying to sum. And we've got three different cases here, what feels like three different cases. We're used to looping and moving through in a very sequential way each index of a list. Well, with a list, we don't have indices. We can introduce our own concept of an index later, but for now we're going to think about processing one case at a time and then leaving the rest of this case to recursion. So what do I mean by this? Well, in this first case, if we were asking what is the sum of this list, obviously it's going to be 0, right? And so this is a very simple base case. If we're asking for the sum of none, then our response is 0, right? So this is a base case. Our recursive case is going to be, okay, well, what is the sum of this list? And when we get a list, we're actually going to get a reference to the first node, or the head node is what we like to call it. This is what we would call the head of this list. We get a reference to this, and what we could say is the sum is going to be, we could think of the sum as, what is this value? So 110 plus the sum of what comes after me, of everything that comes after me, which would be, this value right here, right? And so the sum of this would be, well, we don't know. I'm going to just draw a pointer here, the sum of none. Well, we don't know, but when we actually did this just before, we realized very quickly, oh yeah, that's a base case, that's 0, so this would be 110 plus 0. Our job is done. Now, as the final example here, we ask what is the sum of this linked list? Well, this is our head, and initially this would be sum of the first iteration of this would be 110 plus the sum of what comes after me. Well, what is that? Well, that is going to be 210 plus the sum of what comes after me. Let me get out of the way here. Right, so plus the sum of what comes after me. And well, we know that that's going to be 0. So 110 plus 210 plus 0, and that's going to give us 320, right? So this is where we're going to see this notion that, notice we've got these recursive calls here. So this is where the recursion is happening, where our algorithm is actually going to be very simple. We're going to say, okay, if either we're summing none and it's 0, or we're summing something that is a node, and what we're going to return is the current value of this node plus sum of everything else. And that's a recursive function call, which we'll see in just a moment. So with that, let's actually jump into this example in code, and I'll have you join me and follow along there. So go ahead and set up a file named recursion.py, and we're going to have this in lessons. And the first thing we're going to do is declare our node class. Right? So class node, and this will be, let me actually make this a little bit bigger for you there. And this will be, we'll have a value that's an int. And then as we've just discussed, we're going to have a next value, which is our next node. And this will be a node, but we would have a problem if we said it was just node, right? And it's actually not the problem VS Code is alerting us to. VS Code is saying, hey, this isn't defined yet. Can you remember why? We talked about this a few lessons ago, but in Python, in order to refer to the type that you're defining within a class, you have to do this funny thing from future import annotations, right? But we've got this funny problem here. If next has to be a node, where does it stop? Well, we just learned where it stopped is when we reach a none value, right? So while this list is continuing to link between nodes, there's going to be a reference to another node, another node, another node. But once we finally reach the end, the final node in our linked list, that value will be none. Okay. So we need to establish a constructor. Let's go ahead and define an init. And that init will, of course, have a self parameter, and then have a value of type int and a next of type node or none. And let me get this out of the way here. Just go a little bit larger. And this would actually be a fine point. If you want a good refresher, try initializing your values here. Of course, self.value is value and self.next is next. This is actually all we need to represent a node. So let's try actually constructing a linked list for the very first time. And let's make a note of this. This is where the recursive structure is established. Okay. And node is an example of a singly linked list recursive structure. Cool. So if we wanted to have our, let's say courses list, its type is node, and how would we construct and initialize this linked list? And let's say we wanted 110 to be followed by 210. I'm going to give you a challenge here. Construct a linked list with 2 constructor calls such that 110 is followed by 210 is followed by none. All right, so see if you can construct this. Pause the video here and we'll come back in just a moment. All right, so this is an interesting place where we're seeing a nested. If you did this in one line, it's a little bit more intuitive to do this in one line rather than across multiple, but I'll show you both ways. So we could have a new node, the value would be 110, and the next node would be another new node where the value is 210, and the next node of it would be none, right? And so this is us establishing a linked list. Notice that this constructor, if we think about how this expression is evaluated, we work our way from the inside the parentheses out. So when we're evaluating this constructor call, that's going to be the one that happens first. So we would set up a node on the heap. Its value would be 210. Its next would be none, right? And then we would have a reference to this node, and it would be passed to the outer constructor, and the outer constructor would get 110 as its value, and then the reference to this ID on the heap as its second argument, and this would produce a new node value. Now we could prove to ourselves that we have this, so we could say print courses.value and print courses.next.value, and you're going to see something interesting here. And this is where Python's trying to help us out. Our editor is trying to help us out. It says we might have a concern here. This might not, value isn't a known attribute of none. Well, this is because we use this type union, right? So next is either going to be node or none. We don't actually know. So we could put in an if statement here, but let's actually see what happens when we run this. It turns out this works, but if we were to print courses.next.next.none or .value, of course, there's not a next attribute of 210. The next attribute of 210 is none. So none.value, it has no meaning, and we get this error. And so what we learned in type unions is if we wanted, we could test, if courses.next is not null, none, we would for sure be guaranteed that next has a value. In other words, if we know that courses is a node, and if its next attribute is not none, meaning there is another node which follows me, that's the only other option here, then we can check its value and that'll be fine. Right? So let's actually, one of the things we could do is we could drop a debug point here, or breakpoint, and try this one more time. So I'm going to run this again. And when we break, what we'll see is, courses is a node object, and its next is a node object, but 110 is a value. So we look at what's next. We see that its next value is none, and its value is 210. Right? So we're seeing that relationship being established between these nodes. I'll press play here. So how would we have done this in 2 steps rather than a single constructor call here? Because you could imagine wanting to build this up dynamically. We could imagine, course 210 is a node. That is a node where 210 is none. And notice that we have to actually construct this first in order to change out our constructor call and have a reference to some variable that we established beforehand. Right? So this is a little bit less obvious and it feels kind of strange. You kind of have to build your list from the back out, or from the very base case out. And this is one of those things that feels like you're turning intuition on its head. You mean I have to start from the very last element and construct my list one by one on the way as we're building it up that way? And that is the case for how we're producing a list here, and how we would have to construct a list. And this is what happened when we did it. I'm actually going to leave the example 210 none as was, because this is how we did it here, right? First, Python needed to go construct this very last node, then it needed to construct this one. And you can imagine if we had, node 301 and none. Similarly, this would be the first object that gets constructed. This would be the second object that gets constructed, and this would be the third one. And you kind of, we're working our way down to a base case, right? This is the end of our list, and then building up the list with references on our way out. So how would we actually sum the values of this list using a recursive process? Let's write a recursive implementation of sum. And sure, we can leave an example of this here. So we'll example accessing these attributes, the recursive attributes. And I think it's worth adding this third node here, 301, even though we're not printing out that value, that's okay. So before we introduce a recursive method, let's try introducing a recursive function. There are two sides of the same coin. With what we know about methods, it's just that we would be defining it on the node class, but let's define a method outside of our class, or sorry, a function outside of our class named, let's call it rsum, or let's actually name it specifically recursive sum. There's no reason not to use a full longer name when you have no limitation on the names. And what we're summing is a list, and let's call it x's, and it's type node or none. Right? Again, or this is a union where the union it's the union of node and none. Well, that is node or none, and this is going to return to us a float. And return 0.0. Right? So we've got this recursive sum, and if we wanted to go ahead and try calling this, we could do print recursive sum and give it courses. Now, of course, this doesn't work, right? We're going to get 0 printed out. And let's go ahead and maybe make a little note there so we know what we're looking at. It's 0, right? No surprise. But if we think really briefly back to our intuition here. So I'm going to switch back to my iPad really quickly. Do this. And you'll notice that we had a couple of cases here. We actually only have 2 separate cases, and then we see how recursion plays out. The 2 cases that I want us to focus on are this one. This is our empty list. And what we know is when we sum the empty list, or when we sum a value of none, it's going to be 0.0, right? Otherwise, our other case that we care about is when we sum a non-empty list. So when we don't have a none value as the list that we're trying to sum, we're going to return this list's value attribute, right? So we're going to take the value, 110, add it to the sum of the rest of the list, or the node.next attribute. So we're actually going to sum next, and recursively, this will just play out in a way that hopefully will make sense as we're bringing it together. So let's try implementing those 2 cases. So the 2 cases were if x's is none, we've already got this case handled, return 0.0. Else what we're going to do is return x's dot value plus, and here's where we're seeing a recursive function call for the very first time. Recursive sum x's dot next. Right? And that's it. This is a recursive implementation of sum, of a summation. And what do we see? Well, we see 621, that's 301 plus 210, that's 511 plus 110, 621. We added all three nodes together. If we wanted to, we could convince ourselves, we could change this to 300, and we see that it's now 620, and so on. This is summing this up. And that's pretty cool, right? We are, notice there's no for loop here. There's no loop, so to speak, except that we are recursively calling a function. And one of the reasons why we spend so much time on memory diagrams, and we'll have a diagram where we introduce recursion in it, is that this can feel very nebulous until you think about exactly what's going on in your function frames, right? Every time you have a function call, we add a new frame and we change our parameters based on that call. So notice here, we're calling recursive sum and we are passing in x's.next. That'll be the next value of x's in the new frame that we establish. And we would establish one frame per each node of our list. And we finally stop this recursion. We reach our termination condition when x's is now none, when we've reached the end of the list. So it's like we're saying return, the first node's value plus the sum of everything else. Well, the sum of everything else is the sum of that node's value plus everything else. Well, the sum of that node's value is the sum of what follows it plus everything else, right? And we're effectively saying, I'm going to deal with right now, this function is going to deal with just the node that I was given. And then we're going to let recursion, this call right here, handle the rest of it. That's going to be its problem. And so if the current node is the end of the list, that's easy, right? If the current node is not the end of the list, well, we're going to let recursion solve the rest of this problem. We're going to focus on just the small piece of the problem that we're trying to solve right now, which is how do I sum the current value with the rest of the list. Cool. Now, I think this is another place where seeing this recursive process play out in the debugger is going to be fascinating. So I'm going to drop another breakpoint at line 24 and reload this program. And we see that we're stopped here, right? And so x's has the value 110. That's our first node in the list, right? I also want to pull up this call stack and try and point out where we are here. So here's our sub process, and here's our point in the call stack. So I'm actually going to make my text just a little bit smaller so that we can watch this play out. All right, so we test is x is none, and notice its value is 110, so that's false, or x's is not none, its value is a node object, so we step over that, right? And here we reach this return statement. Well, we've got to call this recursive sum function, so I'm going to use the step into button. So we step into this, boom, and notice we go back to the top of this function, but now our node has changed. Now x's dot value is 210. But notice here's where things are interesting. Here's our call stack. So our call stack had, here's where this is the frame where x's was 110. This is where we just made this function call. And now our new frame that we're processing is this frame where x's is the node with 210 as its value. So we've moved on to the next node, but notice we've still got to return back to these frames. So let's step over this. X's is not none. And now we reach this call and we're going to step into this as well. All right, so we step in and boom, notice we've got a third frame on our stack for recursive sum. This time around, our value is 301. But if we click on these other frames, we could see, oh yeah, the frame that came before it, the value was 210. The frame that came before it, the value was 110, and so on. Okay, so we step over this, and here we reach another recursive call. So we step into that recursive call, and boom, finally notice x's is none. Before we actually process this, notice we've got 4 frames on our stack that we've built up. So we step over this line and we reach a return statement. This is where our recursive process starts to go back up the stack and say, okay, I'm going to return to you the value of 0. So we step out of this and we see coming back to this frame, the recursive sum value that was returned for this particular function call was 0.0. We can see that in our locals. It's just VS Code notes this return value with this return in parentheses. And x's dot value is 301. So when we step out of this, notice we only have 3 frames left. So we finish processing this. Boom. Our recursive sum was 301. and now we only have 2 frames on our stack. Our frame is returned. And here, so this call, when x's was 210, 301 was what was the sum of everything that came after. Boom, we step out of that. Now 511, that's 210 plus 301, 511. X's, notice we're in the final frame where x's dot value was 110 and recursive sum was 511. We step out of that, and boom, we see that the returned recursive sum was 621. We have no more frames because they've all returned. In VS Code, it's taking those frames away. In our diagrams, we just write in the return value and leave them there. But technically, their job is done. So VS Code is removing them from our visibility. And we're back here. We print, and boom, we print that out. So we'll try tracing through this example together. But there's one more example I want to provide you, which is a recursive method definition. And before we go and diagram sum, let's try implementing a stir method of this node. And let's say that we want our representation to be something like, print a stir where it's, our example representation be 110 followed by 210 followed by 301 followed by none is how we would want to represent this as a string. So how can we do this recursively? Well, let's define our stir method. And remember, this is one of those magic methods that returns a string value. And when we print, say, we'll try printing courses in just a moment. Actually, before I finish this implementation, let's just prove to ourselves, we could print courses here. And when I save this, we see, and I remove that breakpoint. So if you have that breakpoint, be sure to remove it. Otherwise, you'll be stopping your debugger. We have, Python's default string representation, which gives us this gnarlier representation here. We want something nicer. So how do we do that? We implement this stir method. And here we have another opportunity to write a recursive method. So the base case is going to be the same. The base case is when we stop our recursive call. So if self.next is none, what's our base case going to be? Well, let's just return none. Else, what are we going to do? And I'll give you a challenge here. Try returning the string self.value followed by an arrow followed by the stir of self.next. Right? So see if you can put into a string format, set up a return statement, and you're going to need to. This is sort of pseudocode, but you want to have the value, which would be the number that this node has, followed by the string representation of what comes after me, which that's going to call this method one more time. So see if you can implement that, and when you do, if you are able to, you should see the list printed out when we printed our string. But you notice right now we get an error because we've still got some work to do. Our else doesn't actually return anything. In fact, we've got a syntax error. All right, well, we can do this in an explicit way. And we could do something like return self.stir self.next concatenated with an arrow, concatenated with, not self.next, stir of self.value, concatenated with stir. I'm actually going to make this an explicit method call, and then now let's keep it simple. Self.next, right? So remember, this is sort of a special function, and what Python is doing with this built-in function is it's going to look at this next object, which is going to be a node, right? We know that it's going to be a node because we handled the case where it wasn't up here. And then it's going to go and call its stir method, right? So this is ultimately going to be the recursive call that calls this method. And we can go see, and 110, 210, none. That's interesting. Why are we not seeing? We've got a logical issue here. So notice we have a little bit of a bug. This is a fun one to try and debug in real time. So we're saying if self.next is none, we print string none. But notice we're skipping over our third element in this list, right? Because this is true for the third element. And so this is where we actually have to be a little bit more careful than down here. Notice this method is only ever going to be called on a node object, right? So this is not the base case. This is what we actually need to have here is something that looks more like this. Stir self.value concatenated with none, right? And the reason is, for this method to be called, we know we're in a node. And so our very last node is 301. And 301's next was none. And so that's why it was followed by, that's why we were getting none printed out before. We were reaching a base case. This is the point at which we stop recurring. But because this isn't a method on the node itself, we're not calling stir on none in a way that we're seeing here. We have this potential concern. So I mentioned that we could show you the recursive implementation of this a little bit more directly. So self.next.stir would be the showing you how we could call this method directly. And this is where you see the true recursion. This feels a little bit more recursive, where we see the direct connection between we're calling this method on the next object, and we see that play out there. This is the method call that was happening behind the scenes. Python was doing this for us automatically. And there's one more interesting thing that I could show you, which is because of this, because we know that we're terminated in none, we actually don't have to handle the base case here. So this will be, let's give this a shot real quick. And we see that this works as well. How does this work without a base case? Well, first of all, for the recursion that we're writing always in Comp 110, we're going to explicitly define a base case and handle it ourselves. But notice that why this would work in this case, but we couldn't have done it down here, is because next, when it's none, next has a stir method defined on it, or sorry, none has a stir method defined on it. We don't see it, but that's what results in none being printed out. So because next could be node or none, when next finally is none, and we call stir on the none type. In fact, we could try this in our interaction here. So none is a value in Python. None.stir gives us none, the string representation. And so when we finally reach that last node and we called next on none, it would result in a string. We're not going to write recursion with that level of assumption. And that's sort of a special case of this toString. It's special that none has a string representation. And so we're going to leave this as shown, where this is another way of handling a base case. Yeah. In the next challenge question, we're actually going to trace through this example and try and get a little bit more of an intuitive feel for how a recursive function is processed step by step on the stack. And we'll go and do that together in the very next video. Great work on recursive structures and processes.